Hello everyone, I'm Dhruv and I'll present our paper AMRA star Anytime Multi-Resolution Multi-Heuristic A star. As the name suggests, AMRA star is an anytime algorithm that searches multiple resolutions of state space discretization, and it can leverage guidance from multiple heuristics when it tries to find a solution. It is provably complete and bounded suboptimal, and it combines these three aspects of search-based motion planning into one general algorithm. The paper talks about how AMRA star might evolve into well-known existing algorithms under specific conditions. But just to talk a little bit more about these characteristics, searching over multiple resolutions of state space discretization can be useful in two ways. One, when you have a local minima represented by the cul-de-sac in this image, you can expand many fewer states at the coarse resolution to find the path that goes around the cul-de-sac and reaches the goal in the bottom left. However, in environments where you must necessarily travel through narrow passageways, AMRA star can also expand states at the fine resolution to find paths to the goal. The anytime nature of AMRA star allows it to find a suboptimal solution quickly by expanding states at coarse resolutions, and then spending the remainder of the planning budget to converge to the optimal solution by utilizing the fine resolution discretization. We can also instantiate it with guidance from multiple heuristics, which is useful because depending on your environment and your robot, different heuristics might be beneficial to you in different regions of the state space. In a 2D grid world, if you use a Euclidean distance heuristic, you might expand many more states than if you had access to a perfect heuristic. The paper provides a thorough quantitative evaluation of AMRA star against relevant baselines, but for the presentation, I'm going to present two qualitative examples to hopefully give you an intuitive understanding of the behavior of the algorithm. So first, we're going to look at a 50 by 50 grid world with a cul-de-sac and a narrow passageway. The start state is inside the cul-de-sac, the goal state is outside, and we discretize the state space at three different resolutions: 1 by 1, 3 by 3, and 9 by 9. The first solution that's returned by AMRA star with a high suboptimality bound of 200 goes around the cul-de-sac to get to the goal. And it finds this solution by expanding states mostly at the mid and low resolutions. So state expansions in these images are shown in blue. Eventually, though, when we need to converge to the optimal solution over time, we must expand many more states at the high resolution in order to provably return the optimal solution. In this case, one that goes through the narrow passageway to get to the goal. The second planning problem is a kinodynamic planning problem for planar UAVs. We're trying to model these helicopters on the right. So we're planning in the X, Y, heading, and linear velocity state space. We generate motion primitives by discretizing the X and Y dimensions at two different resolutions, 3 meters and 9 meters. We utilize three different heuristics for this planning problem, and we're trying to find minimum time paths in grid worlds from the moving AI benchmark. So we want the UAVs to travel as fast as possible for as long as possible. And the state space has roughly 37 million states. So as you can see, the initial solution that's returned by AMRA star makes the UAV travel at lower velocities in some points of the path, represented by the purple color in these images. However, over time, when we refine it to return the optimal solution, the majority of the path makes the UAVs move at as high a velocity as possible. So thank you for listening to my presentation. Our code is online on GitHub, and I can answer any questions about the algorithm, the experiments, search algorithms in general at the poster session. Thank you.